Hi, welcome back. We had an excellent question using, I think, from the problem set, where we had a halogenation mechanism where we didn't get a precipitate. This was a last minute addition to the list, and I like it. So let's do it. And what happens here is because we don't have three H's on either alpha position, we do not get a iodoform precipitate. The question is, which H would you like to take first? Well, I would like to take the H here because if I generate an anion there, it will resonate and make a pi bond here, which is more stable than an anion here resonating to make a pi bond here. So would I be harsh grading that if you picked the wrong alpha H? No, I'd probably take a half point if you grabbed the one on the left instead of the one on the right first. So KOH is really OH minus. And I think instead of crossing things off during review, I should redraw them because that's what you're going to have to do on your test anyway. And there we go. And keeping that in mind, I'm not going to have big molecules on your test when you do mechanisms because I don't want you copying huge molecules out. That's good news, right? And we're going to this alpha anion here. I'll take either resonance form. This one's nice. It's the direct one. And it will attack iodine. I'll draw the iodine. And remember, you don't make triangles this time. And we've accomplished iodination of that alpha position. Now it's time to move to the other side, where we grab an iodine using OH minus again. Can't combine these steps, sadly, because carbon doesn't start with a lone pair, and you can't pretend it was there before it's there, if that makes sense. I hope that makes sense. I've seen students try to do that, and they put the lone pair right here, and I'm saying, okay, really, you just did an octet violation if you did that. So don't do that. Hey, don't draw that again. Done with that. That anion is going to attack II. And we're almost there, aren't we? Oops, R's not over there. Got an iodine. Got an H. And take the H off. Mole number 3 of hydroxide. Going up here. Mole number 3 of iodine. Right here. Lone pair hits I. Doesn't look like a lone pair. There it does. Okay, and that does that. Then moving back to some multiple choice, unless we have a question on that.
I just have a quick question. So
Sure.
for the acid-base halogenation, we're only we're enough with only one halogen on the alpha carbon, right? But with the base, we have to keep moving on until we get all the alpha
If
H's.
you have base, you do what's called exhaustive halogenation, where every alpha H gets taken, and every position ends up with as many iodines as possible. With the acetic acid, you only do it once. Yes.
Right. Thank you.
You're welcome. And then we had a for questions 13, 14, 15, and 16 here. There's a KEQ thrown in there. What I'm going to do here, I'm going to just take this to the next page and we'll just do all the products as quick as we can. And just remember to come back for PKEQ in step 4. And down here. Yeah, in product 2 synthesis. Oh, this one, acetic acid, we want the PKEQ. And let's just run along. I don't think we did this one. I hope not. We have to know what benzyl alcohol is for every test this semester. Oh, it makes me real sad if somebody does this and they think benzyl alcohol is right here. I mean, they're doomed. They won't be losing just points on here. You won't be able to get any of these questions right. That is phenol. Do not confuse it with benzyl alcohol. Benzyl alcohol is here. Benz, B-E-N-Z, followed by something else other than ene, is always one more carbon off benzene. And then if it says benzyl alcohol, what is that one thing off that carbon? It's an alcohol. If it was benzoic acid, I'd put a carbonyl here. If it was benzaldehyde, I put an aldehyde and an H here. Benz is a very common prefix for a lot of things. 1, 2, 3, 4 to product 1. I'm just going to go 1 here. And we're doing phosphorus tribromide converts OH to Br. Lithium converts Br to organolithium. Butanal is a 4-carbon aldehyde. So in step 3, the organolithium's attacking that. We have all the benz carbons present as the nucleophile. I should go with phenyl, shouldn't I? There's benz. And the new bond is from that benz carbon, benzyl alcohol, to, there's the new bond to our O minus in step 3. There's the 4 carbons of benzaldehyde, 1, 2, 3, 4 carbons in benzaldehyde. Step 3 creates an O minus when the organolithium, the C minus, attacks here. You get an O minus, and O minus becomes OH. Very common theme for this test. So you'd pick the product that corresponds to that with nomenclature. And that's 5 carbons. So 1 phenyl, 2 pentanol. And then going up to product X. PCC oxidizes this molecule to here. Oh. Why? Okay, whatever. I just needed more room. Why is it doing this to me? Because I'm not here, that's why. X comes from the ketone created by PCC, making this a ketone, and that will be brominated on the alpha position as discussed just moments ago, 1 time because acetic acid is present. And why do I prefer putting the bromine exclusively on that first alpha carbon and not the other one? And remember, in the mechanism, there's an enol in the mechanism. And enols that resonate with phenyl groups are much more stable than enols that don't. It's not even close. You would get 0% yield of bromine here, 0. So that there is molecule X. Okay, so there you have it. And you're going to go to Y. We'll go backwards to Y. You're making a protecting group with the first step. Do you want to go through each step? I have no problems with that because there's some good review here. Y is going to be way over here. I don't know what I just did. Okay. This is step 1. You're going to put a hat on there. It's a protecting group. This is the most common protecting group for ketones here from ethylene glycol. Yes, that molecule above the arrow with a 1 beside it is called ethylene glycol, if you forgot. DST makes sure the condensation reaction happens with high yield. Similarly to earlier, we're doing organolithium, where we used to have a halogen. Propene oxide is the simplest, one of the simplest epoxides. Looks like this. Has 1 more carbon. It will be attacked on the less substituted carbon. Step 4, get used to this. You're going to get an O- in step 3 because your nucleophile, which will be right here, is attacking this carbon, generating an O-. First thing that happens in step 4, protonation of the O- to make an OH. Aqueous after sulfuric acid means you're also going to deprotect the acetal. So you're going to get your ketone back. So we have phenyl to an alpha carbon that's got a new bond. We'll address that in a second. We got our ketone back during the hydrolysis. And the new bond was to a 3-carbon piece from propene oxide that had O-, which became OH. So that is product Y. You'd have to pick the name that matches that. Nomenclature says ketones more important. So you go 1, 2, 3, 4, or 1, 2, 3, 4, 5. 4 is better than 5. And I think we have a question.
Yeah, did you say that protonate the oxide with the acid?
Protonate the O-. The
Yeah.
O- generated here on this carbon with H2SO4. That is the first use of sulfuric acid.
So we're gonna raise it again.
The second use is as a catalyst for the acid catalyzed hydrolysis.
Right.
There's water everywhere. Okay. So this is a very common technique where you can do, normally we follow attack of an epoxide with HCl, right? That's what we normally do. We've seen it thousands of times. We have HCl here. We have HCl multiple times on this test. It does not have to be HCl. It can be any strong acid or even a weak acid that's less than 16. So we've got that covered. But when I give you the big hint that it's also aqueous, then you're going to probably use an excess of H2SO4 and you're going to do a hydrolysis of this protecting group here. It will happen on test day, I promise. And there we go. So we have product Y, which is a dead end there. Now product 1 gives product 2. Product 1 is going to be first converted to an alkyl chloride where you had the alcohol. That's step 1. Alkyl chlorides created from alcohols using thionyl chloride. This will be a Cl. We're converting the Cl to a Grignard. It will be a MgCl right here, which is a nucleophile on carbon 2. In step 3, we're attacking isobutanol. 4 carbons with a V on the end and an aldehyde, isobutanol. And then acetic acid is going to be used to protonate. Remember I said you could use any acid with a pKa of less than 16? Well, 17 if you want. We got a 5. And then 4 is important because we need this HOAC pKa, second time today, is 5. And we're going from step 3 generates RO minus, not ROL, goes to ROH, pKa 17. That's not a plus sign up there. That's a mistake. They're going to react with each other. So I don't know if that's probably more confusing than helpful. The more important thing is you made a nucleophile down there. The nucleophile attacked isobutanol. Isobutanol became isobutanol with this new bond with a pKa of 17. The acid used to make it was 5. pKeq, the acid at the beginning was 5. The acid at the end is 17. KEQ I could ask for. I don't remember which one I did, but I could ask either one anytime. And there you go, product 2. Product 2 is used to make product 3. I didn't put a 2 on my product. Need a little more visual here. What's happening to product 2? Dihydropyran is a useful protecting group for alcohols. So we are protecting it. And then we're going to do another review reaction. So DHP, and that's 1, and 2, 3, 4. I'll go 2, 3, 4. So you're going to have your phenyl, CH2C, and 2, 3, 4. We're going to make a Gilman. Step 2. Well, let's finish drawing what we have here. We have our DHP protecting group here. If you forgot what it looks like when you're done, it looks like that. And now you've got a protected position. NBS is a benzylic or allylic brominating agent. So what's going to happen here? Is this, put R in black. 2 groups end up on the copper. And this is a Gilman. Steps 1, 2, 3, 4. 1 is DHP, 2, 3, 4. Take the organolithium you made in step 3. Remember, you can't make Gilmans unless you first have organolithiums or Grignards. And then you make it into this Gilman here, which will do something called coupling with ethyl iodide. And aqueous sulfuric acid, what did we use it for before? Didn't use those words exactly, but it's right here, aqueous sulfuric acid. It was used to protonate and then deprotect. Here, it will not be necessary for protonation because coupling does not require an acid. So you take everything that was Gilman, try to keep our colors going here. Phenyl, CCCC, and down to here, new bond from a long time ago. And you're going to have your alcohol back. That's the deprotection. You don't really care about the side product, but if you're keeping score at home, there it is. And the coupling reaction generated this new bond here in, I don't know, some new color, baby blue, to an ethyl group. Ethyl attached to an iodide is it? Alkyl iodide couples with a Gilman. What's a Gilman? We have a Gilman right here, chapter 15. And that, I believe, is product 3. And what's happening to product 3 is many things. Oxidation. And then we're making another acetal. How do I know it's an acetal? I have a diol. And I have a catalyst. And I have a Dean-Stark trap. And I have a carbonyl after step 1. This would be a carbonyl. And is that a dead end? I think it is. Nice. So when you're finished, you have a protected ketone. Trying to keep all the colors so we don't lose track. Although the ethyl's now all green. Oh. Protected carbonyl has 2 bonds to O. Remember, the first part was chromic acid oxidation. How did I know that? This combination of chemicals gives chromic acid, CrO3, chromium 6 oxide, aqueous sulfuric acid, react to make chromic acid. So you got a ketone here in step 1 and you protected it. Remember, there are 3 CH2s between the alcohols. There better be 3 CH2s in the acetal. 1, 2, 3. There's your hat. So you'd pick the product that matched that circle or that drawn thing, and that's product 4. Do we have any questions on that? And that might be a good spot to do a break. And I'll let you evaluate. I will pick up on the email of the student who left more to do after this. I will pick up from there when we get back. And I will see you shortly.